Number Theory, Section 3, Congruences and Modular Arithmetic. Video 2, Modular Arithmetic Proofs. Here's a useful technique you can use when proving things using modular arithmetic. Instead of writing A is congruent to B mod n, this is exactly the same as writing A equals Kn plus B. We're saying that A is B more than a multiple of n. We can use that to prove things such as the example that came up in the previous video. So if A and n are even and B is odd, then AX is congruent to B mod n has no solutions. In the previous video, we looked at 6x is congruent to 17 mod 20, and our program found no solutions for this. Well, let's start by rewriting this. So if AX is congruent to B mod n, we have AX equals Kn plus B for some k. And now I just need to look at A and n as even and B is odd. So if A is even, I can write that A equals 2c for some c, and n equals 2m for some m, and B equals 2d plus 1 for some d. Then I just look at the left-hand side and the right-hand side of my equation. On the left-hand side, I've got AX, so I've got 2CX. And on the right-hand side, I've got Kn plus B, so I've got 2Km plus 2D plus 1. Now this is clearly even, whereas this is clearly odd. Therefore, I can't find a value of x that satisfies the congruence because there's no value for which an even number is going to be equal to an odd number. Here's that written out neatly. So since AX is congruent to B mod n, AX equals Kn plus B for some k. Rewriting A, n and B in terms of even and odd numbers, the left-hand side gives us 2CX. The right-hand side gives us 2mk plus 2d plus 1, which I can rewrite as 2mk plus d plus 1, 1 more than an even number. Therefore, the left-hand side is even, the right-hand side is odd. There can be no value of x that satisfies the congruence. The second example we're going to look at in this video is using exhaustion, so checking every single case of something. And in this example, we're going to write a program that finds whether a positive integer n can be written as the sum of two squares, and in the cases where it is possible, our program will display the squares. Here's an example of a program you could use for this. So we start off by defining a function which is called sum squares, and then we start by looking at values of I in a range from 0 up to the square root of n. We don't need to go any higher than the square root of n because once we square it, we'll go over n. Then we take a second value in the range from I up to the square root of n. Now we only need to go from I because when we're adding together these two squares, if we did j from 0 to the square root of n as well, it would find every value twice. So I is just the smaller of our two squares and j is the larger of the two. Then our program checks if I times I plus j times j is identically equal to n, then it prints out the two squares. So let's try our program out. Sum squares of 41, and that outputs 16 and 25. Sum squares of 43, that doesn't give any output at all. Sum squares of 1105, that gives us three different solutions there, and sum squares of 1107, that gives us no solutions. So, in the answer to the second part of the question, which of the following integers can be written as the sum of two squares, we can see that 41 and 1105 could, but 43 and 1107 couldn't. Now, the next part of the question says that if n is congruent to 3 mod n, show that n cannot be written as the sum of two squares. Well, let's just check. Of the examples that we have here, the two that we found that couldn't be done were both 3 more than a multiple of 4. And the two that we found that could be done, neither of those were 3 more than a multiple of 4. So how would we go about showing that if n is congruent to 3 mod 4, n cannot be written as the sum of two squares? Well, we need to remember that when we're working mod 4, there are only 4 options that n can be. We need to consider the cases n equals 0, 1, 2, and 3. And all I need to do now is to look at the squares. So 0 squared is 0 mod 4. 1 squared is 1 mod 4. 2 squared is 4. But working mod 4, that's congruent to 0 mod 4. And 3 squared is 9, which is congruent to 1 mod 4. So what I've got here is I've got that all of the different values for n squared are either 0 or 1 mod 4. So if I add 2 squares together, I'm either going to have 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. So the only answers that it's possible to get is 0, 1, or 2. If I've got the answer 3 mod 4, it cannot have been from the sum of two squares. Let's see how that might be written out as a proof. In mod 4, we only need to consider n equals 0, 1, 2, or 3. 0 squared is 0 mod 4, 1 squared is 1 mod 4, 2 squared is 4, which is 0 mod 4, and 3 squared is 9, which is 1 mod 4. Hence, the sum of two squares can have values 0, 1, or 2 mod 4. Therefore, if n is congruent to 3 mod 4, n cannot be written as the sum of two squares. In this video, you've learned how to write A is congruent to B mod n as A equals Kn plus B in order to prove statements about modular arithmetic, and you've learned how to use an exhaustive method in cases where the numbers involved are small.